Hello everyone, welcome to PSpice tutorials. In this session, I will be discussing and simulating the input, output and transfer characteristics of an NPN transistor in common base configuration. Let us start with the circuit. Right? So the input signal here is connected across the emitter to base and is called as VEE. The output signal is connected across the collector to base and is called as VCC, and the base therefore is the common terminal. We note that the collector and base currents enter the transistor and therefore by convention we call them as positive currents, and the emitter current is going out of the transistor and therefore it will be negative current. Rin is R1 here and RL will be R2. Before I begin the simulation, I would like to tell you that I am not going to discuss the theoretical aspects of this configuration. In fact, I have already made a video on that and I will leave the link of the same in the description below. I would highly suggest you to watch that video first before you continue this video. Right. Let us now start with the input characteristics. Input characteristics are obtained by plotting the voltage across the input terminals, which is VEB, and recording the input current IE at a fixed value of the voltage across the output terminals VCB. Right? So we are going to start the simulation, but before that I would like to tell you some configurations of the profile I am going to create as well as use in my PSpice simulation. Right. So this is what will be the profile I will be using. If I want a single characteristic curve, as what you would usually see in many of the textbook, I am going to select VEE, which is our input signal, as the primary parameter, and I am going to vary it from 0 to 5 in terms of 0.01 increments. Let us start the simulation. Please note, I will be using the student version of the PSpice software for simulating the characteristics here. I go to File, create a new project here. Let the name of the project be NPN CB configuration. Right? I make sure I have selected analog or mixed AD as the project type, and I will save all my project files into a folder somewhere in the desktop. Right? So after you select the corresponding path of your choice, press OK. You will then be prompted to ask whether you want to create a project based upon an already existing project or you would like to create a blank project. I would select the blank project here. Press OK. This is the schematic window, and here is where I will be placing the circuit parts. I'll start with the transistor itself as the first element. In order to place the part, you need to first left click on the schematic window, and you will then be given a option in the menu called as place. Select that and then select part. I'm going to use Q2N2222 transistor, and you select that. You can look at the symbol here as well. Double click on that and place it here. Now since we want a common base, I'll rotate the transistor, and you can simply do so by pressing R for rotate from your keyboard. So you still see the transistor attached to the cursor. Press escape to remove it from there. Now I have adjusted the zoom so the circuit can be a little more clearly visible. Right? So this will be my emitter, this is the base, this is the collector. I'll continue with the resistors now. So I'll press P from the keyboard, which will enable the place part window, and press R. Select R analog and place it one across the emitter and another one across the collector. Now we need to place the sources. So before I place the source, I would like to take you back to the circuit diagram and show that across the emitter to base, the supply is connected reverse, in the sense the emitter is connected to the negative terminal of VEE and base is connected to the positive terminal. Coming back to the collector to base circuit, collector is connected to the positive terminal of the VCC and base is connected to the negative terminal. Now I go back to the simulation window and start placing the DC sources. So type VDC, select DC source and connect in such a way that the positive of the supply is connected to the collector. So this is fine, but when it comes to the voltage supply across the emitter, I need to rotate it 180 degree. I will do so by simply pressing R. Right? Now the DC voltage sources are also placed. Let them be named accordingly as VCC and VEE, right? So the circuit is almost complete now. I need to connect them, and to connect I will use the wiring. This is the icon which will enable you to place wire, or you can simply do so by pressing W from your keyboard, W for wire, right? Now the components are connected. I now need to place a ground. I will press G for ground from the keyboard and select 0 source and connect that to the circuit as well. Right, now the connection is all complete. Let me start by giving values to VEE and VCC. Let VEE be 5 volts DC and VCC be 10 volts. Now my connection is complete. I'll start the simulation. To start with the input characteristics, as we already have said, input characteristics are a plot of input current with respect to the input voltage terminals, which is VEB. So we note that the voltage across the emitter to base will be negative because of the way in which the supply VEE is connected. Also, the emitter current is flowing out of the transistor, and by convention we have considered that as negative as well. So we expect the input characteristics to appear in the third quadrant. Let us start the simulation. To start the simulation, you need to build a simulation profile. To do so, you need to go to the menu item PSpice, select new simulation profile. You give a name. I will give it as NPN and create. Right, a new pop-up window would appear, and here you need to change the analysis type from time domain to DC sweep, and you go to the voltage source. Make sure the primary sweep is selected. Go to the voltage source here and type the input voltage name, which is VEE. Right, as I already have shown here, I'm going to vary my supply from 0 to 5 volts. Okay, so I'm going to select start value as 0, end value as 5, and I'm going to increment it in terms of 0.01 volts. Press OK. I go back to my schematic. The profile is already created, so I'm going to run it. Right, now the simulation window appears. Here you need to place traces. So I'll go to trace in the menu item, add trace. I want to plot the emitter current here. So select IE of Q1, press OK. I'm getting some characteristic curves here, but this is not the input characteristics, because along the y-axis we have the emitter current, but along the x-axis we have the input signal VEE. So I will change the x-axis, and to do so you need to go to plot menu item, select axis settings, select the x-axis, select the axis variable and change it to VQ1E and press OK. Right, now I'll remove those grid lines. Right, so this is what the input characteristic curves for an NPN transistor in the common base configuration would look like. This would be our origin, okay, and here we are applying one voltage, and the transistor would trigger at around somewhere minus 0.5 volts. Right, and since both the input voltages as well as the input current are negative, the plot itself is appearing across the third quadrant. Now, in order to plot multiple characteristic curves, I need to perform a nested loop operation. But before I do that, I will show you the profile settings for the nested loop. Right, so this is what is the profile settings. So the primary variable will be the same, which is VEE, but the secondary variable will now be VCC. And I am going to vary it from 0 to 100 volts in increments of 50 volt. Please note that this in fact should be 50 volt here. So I am going to go back, and directly from the simulation window, I select the simulation menu item and select the edit profile. Now I add the secondary sweep. It should be a voltage source only. I will now add VCC. As I said, I am going to vary it from 0 till 100 in increments of 50. So I will get 3 different plots, one at 0, one at 50 volts, and then incremented further at 100 volts. So let us apply, press OK, run the simulation again. We'll once again go to trace, add the trace, which is our emitter current, and then I continue to change the x-axis as well, and I'll select VEB. I will once again remove those grid lines. Right. So this is what the input characteristic curves, in fact multiple curves for different values of the output terminal voltages would look like. Once again, we are obtaining these curves in the third quadrant only. Right. So that is about the input characteristics. We will now continue to output characteristics. Output characteristics are obtained by plotting the voltage across the output terminals VCB and recording the output current IC at a fixed value of the input current IE. Right. So since we have three different regions of operation in output characteristics, I have defined three different profile settings. I'll start with the cutoff region first. So in the cutoff region, I am going to vary VCC as the primary voltage source and VEE as the secondary voltage source. The primary voltage, which is VCC, is varied from 0 to 10 in terms of 0.01 volts, and the secondary voltage is varied between 0 to 0.5 volts in terms of 0.1 volt. Let us go and create these settings first. I go back to my simulation profile. In the primary sweep, I need to now change it to VCC, and I am varying it from 0 to 10 volts in increments of 0.01, no change there. I then go to my secondary sweep. I am going to change the voltage source now to VEE, and I am varying it from 0 to 0.5 and is incremented in terms of 0.1. Right? We'll apply, press OK. Let us run the simulation now. Right, so since we are now trying to plot the collector current, we will add the trace for the same. So IC of Q1 is selected here. X-axis is VCC. I need to change that. So go to plot, axis settings, axis variable. I need to now select VQ1C and press OK. Right, so this is what you would obtain, and you should note that this in fact is under cutoff region. If you wonder how, you can look at the values of the currents here. It is 4 microamperes, 2 microamperes, and here we are starting from the origin 0. You may also ask, in what quadrant are we obtaining these characteristic curves? In order to do that, I'll come back to the circuit again and show you that the VCC is connected in such a way that its positive terminal is connected to the collector and negative terminal is connected to the base. So therefore, the value of VCB is always going to be positive. Plus, the collector current is flowing into the transistor, and therefore by our convention that is also positive. So we will obtain the characteristic curves in the first quadrant itself. Right. Now, if you ask how did we obtain these characteristic curves, the idea and the trickery lies in fact in the profile settings. What I have done here is the secondary, which is VEE, is varied only between 0 to 0.5 volts. Let us come back to the circuit and see. When I apply a voltage of 0 to 0.5 at maximum, the voltage is not sufficient enough to forward bias the base to emitter junction. If the base to emitter junction is not forward biased, the transistor will never go into a biased mode. That is why I have restricted the value of the VEE to a maximum of 0.5 volts. Now let us continue and show the characteristic curves for the active region. In order to obtain the active region, the settings are something like the base to emitter voltage should be forward biased and the collector to base should be reverse biased. Right? So in order to obtain that, I am going to change my profile settings into some new values, and I have given it here. The primary is going to remain the same, but the secondary voltage, which is VEE, is now varied between 0 to 2 volts. In order to understand how this combination will send the transistor into active region, we go back to our circuit and we will see that a 2 volts is applied, a positive 2 is applied across the base, and therefore the base to emitter junction will be forward biased. Now let us go and simulate the same. I'm going to my simulation and edit the profile once again. The primary sweep variable will be VCC and the values will remain the same, no change there. Whereas the secondary sweep, which is VEE, I'm going to vary it now from 0 to 2 volts and I'm going to increment it in terms of 0.5 volts. So I'm going to get 5 graphs. One is starting from 0, 0.5, 1, 1.5 and 2. Let us apply this and press OK and run the simulation. Once again, I'm going to add the trace of the collector current. I'm going to change the x-axis from VCC to VCB. Right. Now you can see the transistor is now operating in the active region because of the flat lines it has produced for the collector current when the voltage across the collector to base is varied from 0 to 10 volts. Finally, I'll show what will happen if you try to send the transistor in the common base configuration into saturation mode. In order to send it to saturation mode, we once again go back to the circuit and analyze the circuit here. You should note, when a transistor enters saturation, both of its junctions must be forward biased. That is, the collector to base must be forward biased, so is the base to emitter. In order to make this happen, the voltage across the collector to base terminals should be less than that across the base to emitter terminals. Now, since our voltage across the base to emitter is varied from 0, the only way possible in order to get a saturation characteristic curve for this particular transistor configuration is to apply a negative voltage across the VCC. Now, since for any practical DC device, it is not possible to connect it in this way and still apply a negative voltage, the saturation characteristic curves for a common base transistor configuration are not practically derivable. However, since this is only a simulation, I can in fact by using the simulation profile vary the voltage across the collector to base and give a negative voltage there. I am going to do so by going once again to the simulation profile and sweeping the VCC from -2 to 10 volts. So now when I make this small variation, I will note that I am going to obtain a saturation characteristic curve as well. So let me add the trace. I am going to add the trace for collector current and I am going to change the x-axis to VCB. Press OK. Right. From this characteristic curve, we note that the saturation region lies in the negative x-axis range. Therefore, we state that for a practical application, this characteristic curve is very difficult to attain. However, in the simulation, you can obtain because there you can vary the value of the DC source between negative and positive voltages. Right. With that, we end the discussion and the simulation of the output characteristics. Finally, we move on to the transfer characteristics. Transfer characteristics is a plot of the output current or the voltage across the output terminals, which is VCB, with respect to variation in the input terminal voltages, that is VEB. In order to once again obtain the same, I have created another simulation profile and the settings for the same are as shown here. So since we are only going to vary the voltage across the input terminals, I will only vary input signal here and I am varying it only between 0 to 2 in increments of 0.01 volts, and I will be recording either the output current IC or the voltage across the output terminals VCB. So I am going to my simulation profile once again and I am changing the simulation profile settings. First and foremost, I will remove the secondary sweep because it is no more required. Select the primary sweep, select the variable, it has to be VEE here, and vary it from 0 to 2 volts in terms of 0.01. Press apply, press OK, run the simulation. Now we add the trace of the collector current. So I am supposed to select IC of Q1. Then I need to change the x-axis, which is showing VEE here, into VEB. So I'm going to go to plot, axis settings, variable VQ1E. Press OK there. Now you will see we have obtained the transfer characteristic with respect to the output current. Now I will also show you the transfer characteristic that you would obtain when you try to plot the voltages across the output terminals by varying the voltages across the input terminals. So in order to do that, you go to plot, add plot to window, select that plot, make sure you have selected this and you can recognize it by looking at this icon. Okay. Now go to trace, add trace. what you are going to add? You are going to add the voltage across the collector to base terminal. So it will be VQ1C. Double click on that. Right. So now we have shown the transfer characteristics in both ways possible. The upper plot is the variation of the collector to base voltage with respect to emitter base voltage, and the lower plot is the variation of collector current, which is IC, with respect to emitter base voltage. Right. So that is about the transfer characteristic curves. Well, that brings us to the end of this session. To summarize, we discussed the input, output and transfer characteristics of an NPN transistor in common base configuration, and we in fact simulated the same for the circuit. If you like this video, press that like button and leave a comment. If you want to watch my future videos as well, you can always subscribe to my channel. Well, that's it from this session. Thank you for watching. Have a good day.